Now, I will tell you about the oscilloscope. Okay. And in oscilloscope, before I show you the actual functioning of the oscilloscope and the purpose of this individual controls which you can see over here, okay, let me just go over to this to the writing pad, and I can just briefly explain that what is there inside an oscilloscope, because perhaps that will give you a better understanding as to what is there inside, and then you will be able to appreciate the controls of the oscilloscope in a better way. Here I will tell you that what is there inside an oscilloscope. Essentially, oscilloscope has got a CRT. So, this is the CRT, and here there will be a cathode, and there will be some heaters, okay, and this will emit electrons, okay, and the electron has to ultimately, the flow of electrons will be so that when the electron ultimately it reaches this screen, okay, this screen is actually coated with phosphors. So, that means to say that when the electron beam that hits the phosphors, then it illuminates. Okay. But what we are using, this instrument we are using for the purpose of observing the waveforms of various circuits. Okay. So, we want to keep the waveform that at least it should be visible to our eyes. So, if the electron beam hits at one particular point and the and immediately it shifts to another point, and that point gets illuminated, like that we will not be able to make out anything, because then that bombardment of the electrons with the phosphors, that will take for such a brief time that we will not be able to see anything. So, these phosphors are actually made of materials which are having significantly high persistence. High persistence means at least to the extent that our eyes can integrate a feeling of, as if to say, a waveform has been fully shown, okay, from the left hand side to the right hand side of the screen, and we should be able to see the waveform properly. That is the idea which we want to have. So, that is why these phosphors are made with good persistence of vision. Okay. Now, if say we heat this cathode, okay, using some heater coil, okay, in that case electrons will be emitted and electrons will flow directly, and it will hit only the center of the screen. But obviously, we do not want the electron beam to hit the center of the screen all the time, because there the problem will be that in no time, I mean, if a continuous electron beam is hitting the center of the phosphor screen only, in no time the phosphor at that particular point will burn out. So, we will have a center burning effect. So, what we have to do is to properly direct the beam in whichever direction we want to, and to do that we have some deflection mechanisms in the CRT. So, we have some deflection plates, or it can be done using deflection coils also. So, deflection coils or deflection plates, whatever it may be, okay, say we have one set of deflection plates or coils kept like this, and exactly 90° to it. So, if one is directing it horizontally, the other pair of coils or the other pair of plates, okay, that will direct the beam vertically. So, one set of plates or coils directs it horizontally, another set directs it vertically. So, that using the combination of the horizontal plates and the vertical plates, it is possible for us to move the beam to anywhere in the screen. So, what we do is that, supposing you think that only the horizontal coil is existing, okay, supposing only the horizontal coils are existing. So, what happens is that using this horizontal coil, supposing I change the voltage from some negative voltage to positive voltage. Say I apply a waveform like this, say this is my DC level 0 volts, and supposing I apply a waveform that goes from say minus something, say minus 1 volt or minus 2 volts to plus 2 volts. Okay. Now, what happens that when it is minus 2 volts, the coil voltage is minus 2 volts, it will direct the electron beam to the extreme left possibly. And when we give plus 2 volts, then the electron beam will be directed to extreme right. So, if I continuously keep changing this voltage from minus 2 volts to plus 2 volts continuously, then it will go from the left hand side to the right hand side. Again, after it goes from minus 2 volts to plus 2 volts, if I immediately bring back the voltage to minus 2 volts, then what happens? Then the electron beam goes to the extreme left hand side once again. So, when we observe on the screen, we will be observing something like this, that supposing I draw the screen only and say that this is how the beam moves. Okay. So, with extreme negative voltage, the beam is here, and then when it is 0 volt, it comes to the center of the screen. When it is plus 2 volts, it goes to the right hand side of the screen, and as I had shown here that from plus 2 volts we are immediately bringing the voltage to minus 2 volts, which means to say that once the beam reaches this extreme end, that is extreme right hand side end, the beam is immediately brought back to the extreme left hand side end. And if we have a waveform that goes like this continuously, that means to say that after it reaches plus 2 volt, it is suddenly brought back to minus 2 volts, and then once again it increases linearly from minus 2 volt to plus 2 volt, then again a drop like this, then again like this. Can you see that this waveform that we are drawing, that looks like a sawtooth, right? It looks like a sawtooth. So, we call this thing as sawtooth voltage. Okay. So, we apply horizontal on the horizontal plates or on the horizontal deflection coils, we will be actually applying a sawtooth voltage. So, that what we are doing is that the beam we are bringing from the left hand side to the right hand side, that is changing linearly, and then once it goes to the right hand side, immediately it is brought back to the left hand side. But what happens is that in practice it is very difficult to generate such a sharp fall. Okay. No matter whatever good electronic circuits you may try out, there will be some finite time which may be there, like I may have that up to plus 2 volts it goes like this, and then maybe a few microseconds or so it takes for it to come down from minus 2 volts to plus 2 volts. So, then what happens? Then that amount of that finite time which may be there, however small it may be, you will be observing as if that the beam, okay, the electron beam, while retracing, there will be a faint trace that is left behind. Okay. Actually, the oscilloscope circuit is so adjusted that this part of the waveform, which is called as the flyback time, during flyback time the screen is blanked out, so that you cannot see the beam retracing backwards. Okay. So, all that we are going to see in the screen is that a straight line. Supposing we feed a signal like this onto the horizontal plate only, nothing in the vertical plate, we will see a continuous straight line, that is that will be shown. Okay. Now, how do we display the waveform then? Because we want to display a sine wave with which we are carrying out the experiment. So, what we do is that there will be another set of plates, okay, which will be there horizontally. So, I mean because it is a 3-dimensional thing, means there will be another set of plates which will be just at right angles to this, okay, which we can use as the vertical deflection plates. So, now we keep applying this kind of sawtooth voltage, or this is also referred to as sweep voltage. And why is it called sweep? Because you can see that it is sweeping the electron beam from the left hand side to the right hand side. So, it is also referred to as the sweep voltage, and we do the sweeping using sawtooth. Now, when it is actually going to the right hand side, if at the same time we apply, let us say, a sinusoidal voltage at the vertical deflection plate. Then what happens, that the beam movement in such a case will not be exactly horizontal like this, okay, because the vertical deflection plate will now influence the journey of the beam. So, as the sine wave voltage changes, supposing the sine wave changes from positive from 0 voltage to the positive voltage, and then it again goes to the negative voltage, then it will trace out like this. The beam itself will make a journey of this nature, so that you can see what you will see on the oscilloscope screen is a sine wave. Okay. And if, say, for example, I just give you a figure that supposing this sawtooth voltage is operating at 1 kilohertz frequency. Okay. So you can say that it will take 1 millisecond to complete its journey, right. Now, we also apply another 1 kilohertz sine wave. Supposing it is a 1 kilohertz sine wave that we apply over here. So, you will see that this also takes 1 millisecond. So, in 1 millisecond of time, when the beam goes from left to the right, this sine wave also completes one cycle, so that you will see exactly one cycle of a sine wave. Now, instead, if you are feeding, let us say, if you are feeding a 2 kilohertz sine wave instead of 1 kilohertz, then what happens? Then you will be seeing 2 complete cycles of a sine wave. Why? Because 2 kilohertz means it is 0.5 milliseconds, so that we will be completing 2 cycles. So, it will now look like this, that if I show the screen once again, okay, then it will be that this is the horizontal line, this is the middle. So, within this there will be one cycle, and then again from here to here another cycle, so that 2 cycles will be there. Now, I tell you that supposing it is not 1 kilohertz or not 2 kilohertz exactly, supposing it is somewhere in between, say it is 1.3 kilohertz, and we want to show the waveform. So, obviously, you can well understand that 1.3 kilohertz means, and with the sweep still existing at 1 kilohertz, okay, we will not be able to show the complete waveform. So, then what happens, that perhaps a part of the waveform will be shown like this. Okay. Say I draw another kind of situation where we will be having, say this is the screen, and say a sine wave is traced like this, that it goes from here to here, okay, and say here it just makes some incomplete cycles. So, it ends here. So, where the beam will be? The beam will be here, and but the sine wave is a continuously running sine wave. So, what will happen is that it will start, I mean the next journey it will start, because the sweep will bring it back immediately to this place, okay, and the next journey will start something like this. So, if the point from which the sine wave starts, okay, that changes with every trace, okay, and since the traces are happening very fast, what you will see on the screen is that, as if to say nothing is stable, okay, the waveform is running around, okay, in its own way, and we are not able to make it static so as to take any readings with the measurement. Okay. So, what we do for that purpose? Actually, for that purpose, the oscilloscope has got certain very sophisticated features which are called as the triggering of the oscilloscope. Okay. And there are some trigger controls also available, and using the trigger controls we can exactly make the waveform, okay, going from one place to another, and only with the signal it gets triggered, so that it just starts the next journey from the same starting point once more, so that we will observe the waveform like a static waveform. So, this is called as a triggering. So, this is another beautiful feature of the oscilloscope, because without triggering it will not be possible for you to take any measurements. Okay. Now, what happens is that, so we have the sweep voltage on the horizontal side, okay, and for the vertical deflection plate you just have to feed whichever voltage you want to monitor. Okay. If you are monitoring a sine wave, feed a sine wave. If you want to monitor a triangular waveform, feed a triangular waveform. If you want anything else, just feed that particular signal, whichever signal you want to use. Okay. And many times what you would like to do is that you would like to simultaneously observe the input and the output of the circuit. So, what we do? If we have a single beam available in the oscilloscope, that becomes a very difficult thing, because with single beam how many times shall we switch over? I mean, once show the input, then again take the jack out and then give the output. So, keep seeing all the time, that will be very inconvenient, because we may like to compare the input with the output. So, that is why the oscilloscope beams are made as multiple beam, and the ones which you will be mostly using in the in the laboratory, they are all dual beam oscilloscope. So, dual beam means there will be two similar beams, okay, two sets of beams which will be available, so that to the beam A you can feed the input signal, and to the beam B you feed the output signal, or whichever point you want to use for comparison, so that you can have a direct comparison between two beams. And the sweep, that makes a very common control of both the beams. Okay, both the beams will be having identical sweep voltage operating, so that both the beams, beam A and beam B, they will operate with identical time scale. Now, this sweep voltage that I was discussing little while back, if instead of 1 kilohertz you make it 10 kilohertz, then what happens? Then the travel time of the beam will be faster. So, then we will be able to show those kind of waveforms, okay, where its time period is much less. 10 kilohertz means the time period will be only 0.1 milliseconds. Okay. So, whichever waveforms are fitting well within that, you can show those things. So, by varying this sweep frequency, it is possible for you to make a timing adjustment. Okay. So, if you are adjusting the knob of the sweep voltage, actually I will show you the controls, okay, the timing control. The timing control, actually it is done in steps, okay, that you can have 0.1 milliseconds per division, you can have 1 millisecond per division, 10 milliseconds per division, 20 milliseconds per division, like that. There are, I mean, there is a knob which will be able to control, which I will come soon to that. Okay. And on the other side of it, wherever you are having the I mean the signal, the actual voltage you want to monitor, which you are feeding to the vertical axis, there you may like to adjust its voltage, because you may like to cover the entire screen, or supposing you want to show a part of the screen only, because whenever, especially whenever you are using both the beams together, okay, you may have to adjust both the amplitudes as smaller amplitudes, so that you can, I mean, in one screen itself you can compare both. So, accordingly you can vary the voltage, which will be used only for showing on the oscilloscope. I mean, you are not changing your circuit voltage, but for displaying purpose you are adjusting the voltage settings, so that how many volts you are showing in every one small division of the oscilloscope, that can be shown by the voltage adjustments. So, the major things which will be there in the oscilloscope is the adjustment of these voltage knobs, which will depend upon what voltage you are really feeding from your experimental setup, okay, and then the timing, which again will depend upon which frequency waveform are you showing from the setup, okay, and the triggering. These days the most of the modern oscilloscopes, they are having auto triggering facility. So, if you are doing it with auto, 90% of the time you will not be facing any problem, but in case you face problems, there are manual adjustments of the triggers that is also available. Okay. So, let me now go over to the oscilloscope, okay, and we will feed the signal from the signal generator, which I have already explained to you, and then you will be able to see that how we can exercise all these different controls, timing adjustments, voltage adjustments. Actually how we do it, that we will show after going near the oscilloscope.